So I give the word to the president of the jury, to launch this Ph.D Defense, and so we can proceed and start.
Yes, sure. Okay, so thanks for inviting me to be the president of the jury. So I'm happy to give the words to our Ph.D candidate, Mohammed Ismail, and let me present his work here for introduction from Staples.
Okay. So good afternoon, everyone, and welcome. My name is Ph.D. I welcome you to my Ph.D Defense entitled Learning-Based Reinforced Control Strategies for Autonomous Vehicles. So in the beginning, I will kickstart my presentation with a quick outline. So I'll first start by stating the main context of the work, and then the main problem we are addressing, and then I'll jump to talk about the contributions that we have made throughout this thesis. The first part for longitudinal control, and then I'll move to the lateral control task, before I talk about the coupled and coordinated lateral and longitudinal control to achieve autonomous driving. And finally, I end with one last contribution using learning-based control for a more advanced and complicated control task, which is autonomous racing. And then I conclude my presentation with conclusions and perspectives. Okay, so as you all know, in today's world, the number of cars is exploding. And this is hugely degrading traffic conditions, so there's a lot of traffic. And in fact, if we pick the example of Paris, a normal person spends around 500 hours just to commute between home and work. That's nearly 23 days. So that's a lot. And on the other side, this ever-increasing number is also causing car accidents constantly. In fact, nowadays, it's yielding nearly 1.35 million deaths on a yearly basis. And what's funny is that in the US, 94% of it is due to human error. So that's bad driving. Also, there's another problem of air condition. And we see there is degraded air condition, there's so much air pollution. And one thing we should say is that if you pick only the transport sector, it contributes with about 20% of greenhouse gas emissions. And the EU, this is yielding at least 100K deaths on a yearly basis. So thinking about these problems, autonomous driving as a concept presents itself as a prominent solution to most of these problems. But autonomous driving itself is a complex problem. It's a complicated problem because there are so many modules that work in a coordinated manner and where they need each other to complement the work. Starting with perception all the way to planning, decision making, to control. And speaking of control, in such cases, simple classical control methods are not enough to cope with the nature of the environment where autonomous vehicles work, because it is constantly changing and it's very dynamic. We have seen lately the emergence of the AI field with very promising results and huge advancements, but still such methods are still regarded as not fully safe due to their black box-like and indeterministic nature, which cannot guarantee certain physical properties such as stability. And so the main aim of this thesis is to be able to use the perks of AI with their huge advancements and combine them with classical control theory to develop safer, adaptive, more intelligent controllers able to cope with the changing environments where autonomous vehicles operate. Okay, so I'll start by speaking about the main thesis contributions. So for the longitudinal part, we propose an approach using self-adaptive PID to control the longitudinal dynamics of the vehicle, that's the speed, using two different approaches. NNPID, which is based on a neural network, and GIPID, which uses a genetic algorithm. And then we move to work on the lateral control. And so as we move throughout the contributions, we increase the complexity of the task. And here, such applications are applied for path tracking, for instance, we propose an optimized adaptive MPC to handle the steering control, and an NPC based on neural networks, and a Memphis MPC controller based on adaptive neural inference systems for this control task. Then, we propose another approach that coordinates both lateral and longitudinal control using LPP MPC for lateral control with BISO PID for longitudinal control, speed regulation. And this coordination allows us to achieve autonomous driving. As we increase in complexity, we move to use another approach which is a little bit more elaborated and couples both lateral and longitudinal dynamics instead of coordination, using an enhanced LPP MPC. And then finally, final contribution based on learning-based nonlinear model predictive control, complemented with a nonlinear moving horizon estimation for the more complicated task of autonomous racing. So starting with the longitudinal control, first we have to model our system, and as you can see here, the system is composed of many subsystems. The whole system contains so many subsystems that work in a coordinated manner. Starting with the vehicle body, which can be modeled as a single point mass through equations that model the traction force, gravity force, air drag force, rolling resistance force. Then we have the wheels and tires, and the tires are very important, usually modeled using the Pasivka magic formula through experimental, it's an experimental approach, so it's modeled through experimentation. And then we move into the wheel dynamics, which translate the gear torque into traction force using these equations. Then we have the differential drive, which for electric vehicles, it's a single-speed transmission system that translates the torque and the rotational speed of the electric motor into torque and rotational speed of the gear. And then we have the most important part, the engine and also the battery. So the engine here we have opted for a static modeling approach, utilizing the electric efficiency map. So that's a data-driven approach to model the engine, whereby we have this map that links the RPMs of the engine with the required electric torque. And then the battery can be modeled, as you can see, as a resistor in series with an opposite voltage, and it powers our engine. Finally, we have the brake dynamics, which if you opt for a disc braking system, it is given by this formula that gives the braking dynamics, the braking torque required, which is in function of certain parameters such as the number of pads, disc braking radius, etc. And we come all the way to the controller, which ensures good tracking. So the controller, for this part, we have opted for the simple PID. Due to its simplicity and ease of implementation, and as you can see here, I have provided both continuous and discrete formulas of the PID. So it's a classic control approach based on the proportional, integral, and derivative actions. The signal that is generated is then translated either into acceleration or braking. But the problem with this type of control is the gains. It's very hard to tune those gains, especially when you have changing working conditions. For this, we propose a first approach to optimize and better tune those gains using genetic algorithms. And so, as you see in figure 1, we apply the PID controller to our plant, the full longitudinal model that we discussed before, and we add on top of it a genetic algorithm that will only look at the mean squared error of the speed tracking, and then predicts the best optimal gains. So this is in function of the changing working conditions, starting with the disturbances and also the varying parameters of the model. And so we perform so many simulations doing these optimizations, which will allow us to generate a data set of the most optimal gains that we can use with their corresponding working conditions. As for genetic algorithms, so they are a biological evolution process by which genes evolve through generations. And so the basic algorithm starts by initializing a population of possible solutions, which we call genes or candidates, then evaluating the fitness of each possible solution until it reaches an optimal criteria. If not, then if the solution in question is not optimal, then it starts performing operations on it, such as selection process, crossover, and mutation, which are genetic operations illustrated in figure 3. And as you can see, if we speak about briefly and crossover, you only pick two solutions and then you mix the codes between them to generate new solutions. If you want to perform mutation, then you pick one solution and you alter its code as illustrated here in binary code to obtain new solutions. And then comes the adaptation phase. So once we have this data set, what we can do is call this data set whenever we are applying our controller. We make use of the known working conditions to decide what are the most optimal gains that fit the situation at hand. We do this using a simple lookup table approach with minimum Euclidean distance. Now to the second approach. In the second approach, which we call NNPID, we implement the PID with a neural network directly on top of it, and as you can see, contrary to JPID, all we need to know here is only the tracking error and the control signal of the PID. And we make use of the backpropagation feature using gradient descent to learn how to optimize those gains. So with this approach, we are able to optimize and adapt the gains in real time, and at the same time, we are able to learn how to change them, and like we do with the genetic algorithm. In figure 2, we illustrate the type of neural network that we use. So it's a simple 3-layer NLP neural network with one hidden layer. For inputs, we have only the error, the tracking error, and the control signal. No need to know the disturbance or any other information. And it produces the 3 gains. And then we just perform the normal backpropagation process, applying the chain rule and backpropagating the error all the way through the network. And one thing is important is that when we are backpropagating the prediction error from the output layer to the hidden layer, there is certain important terms that appear. The one in the orange box here, delta U over delta O, with O being the gain in question. Actually, it is here where we do employ the equations of the PID, as you can see, which is illustrated in this set of equations. So these equations are obtained from the PID formula, and they allow us to tell the network how to adapt and change the gains to further optimize the control performance. Finally, what we do is we test and evaluate, first of all, the GA-PID approach for 3 scenarios. A varying speed profile without disturbance, without any wind speed or any road slope. That's for scenario 1. For scenario 2, a varying speed profile subject to wind varying speed and road slope, shown in this figure right here. So, and the last scenario is we perform multiple optimizations with the genetic algorithm for different speeds varying between 0 to 13 meters per second, different road slopes, and also different wind speeds. And this allows us to generate a data set. And the idea is that we will be able to compare the NNPID approach, which is more general, to the GA-PID approach. And these are the results that we obtained. So between scenario 1 and scenario 2, as you can see, the speed tracking for scenario 1 is better than scenario 2. That is because there is no disturbance. As long as we introduce road slopes and wind speeds, then response time increases and we tend to see some oscillations due to the introduced perturbation. This is even confirmed in figure 2 when you look at the tracking errors for both scenarios. What's important here is the adaptation of the control signals, which is shown in figure 3, that shows acceleration and braking for both scenarios. Scenario 1 on the top half of the figure, where there is no disturbance, you can see that the control actions are smooth, there is no adaptation happening here, whereas when we move into the bottom half, you can see that there is a lot more adaptation happening, represented by the oscillations, and this is due to the introduced perturbations. And then we compare GA-PID of scenario 3, which is general, against NNPID. And we see a similar trend here, so NNPID and GA-PID both are able to track the velocity profile. But when we zoom a little bit on the first part, you can notice that NNPID is a little bit more aggressive, a little bit faster, teeny bit faster. And on the second zoom, you notice that GI-PID is a little bit more affected by the disturbances. So we can say that NNPID is more robust, faster, but more aggressive at the same time. And this is further illustrated in figure 3 when you look at the control actions. For NNPID, as you can see, there is so much more adaptation happening here. And why? Because in the equations of the neural network, we look at the instantaneous change of error. And so whenever there is a change in the error, there is adaptation happening. Whereas in the second half of the picture for GIPID, it really depends if we have optimized for that case or not. So it's less generalized. What we can say about this approach is that GIPID provides better tracking performance and smoother response compared to LLPID, which in turn it's more robust, but more importantly, it's able to run online, so it provides a learning feature online, and also more generalized, but more aggressive. One downside to GIPID is the heavy computations required for the optimization phase. Now we move to the lateral control problem, and we start by modeling the lateral dynamics as we usually do longitudinal dynamics, and here we opt for a simple bicycle model through Newton's laws of motion, which generate this set of equations representing the dynamics. So it's the basic standard bicycle model, which then transforms into a state space model as follows, with state space state vector xc, output vector yc, and control signal u, which is nothing but the steering angle. And the matrices are given as follows. Okay, now for the lateral control, as we said, we opt for non-predictive control. And why? Because of its interesting features. The first one is that it's able to implement constraints on states and control signals. And the second one is its predictive feature that is able to foresee the behavior of the plant into the future. So we start by the same illustrated model in the beginning, we discretize it, and then we augment the state space by adding an integrator and the output. And thus the state space representation matrices become as follows. They become augmented as A hat, B hat, and C hat. And the idea here is to run this equation to predict the behavior of the plant, where F represents the future prediction matrix, phi the future control matrix, and vectors y and delta u are the future outputs and future control sequence, which are given as follows. Finally, we just formulate our MPC controller in the form of a constrained convex optimization problem as follows, where the idea is to minimize the cost function j that penalizes the tracking error with weighting matrix q, and the control effort with weighting matrix r. The rest is just the system dynamics and the constraints applied on the control signal and the output. What we further propose to do is use Laguerre functions to approximate the control signal. And why we do that, it's because it greatly reduces the computation time and simplifies the problem. And Laguerre functions are represented in their discrete time by these terms. As you can see, there is only one parameter that is common, which is alpha, the scaling factor, and also n, the number that of Laguerre terms that we want to use. The feature of Laguerre functions is their orthonormality, where we perform multiple multiplication between different terms, then a lot of the terms cancel out. And so this eases the calculation problem. And so if we want to find the control increment at instant k plus I, then we just need to represent it in the form of Laguerre function representation, which is nothing but the sum of coefficients multiplied by Laguerre terms. So if we want to find delta u, all we need to find is this vector eta that contains the coefficients c1 through cn. To do this, we apply the Hilbert's quadratic programming solution. Other methods include prime dual and Lagrange multipliers. Okay, so far we have formulated our controller. We move into the optimization and tuning of our controller. And to do this, it is very hard to tune different parameters at the same time. So we propose automating this process by using an improved particle swarm optimizer. And particle swarm optimization is another evolutionary algorithm that mimics the behavior of animals such as bird flocks and fish swarms. And the idea is really, it resembles a lot the genetic algorithm. It starts by initializing a population of a lot of particles, evaluating their fitness, updating the population until it meets a certain termination criteria. The algorithm is governed by the equations in the blue box. And so if we are speaking about an n-dimensional problem, then we would have two main vectors, one with n velocities and one with n positions. And the idea is to compute at each iteration the velocity that will move our particle in question from one position to another position in a way that it is closer to a global solution. And this is reflected by the first and second equations of this set. You can see that the first one gives us the velocity, the second one just updates the position. If you further observe the first equation, you see that we have certain parameters such as omega, C1 and C2, which are the inertia weight, cognitive acceleration coefficient, and social acceleration coefficient. Furthermore, we have parameters such as PV and GB, which represent the best local solution of the swarm at the current iteration, G, and the best global solution in all of the swarm, which is GB. So what we propose here, generally these parameters are constant, most of them, in the classic algorithm. Other improved versions are reported in literature which make use of a dynamic alteration, for example, of the inertia weight as represented by the equation in the orange box. So this one, what ideally it does, it reduces the inertia weight from the maximum value omega max to omega min based on the number of iterations, or the number of actual iteration G and the maximum number of iterations capital G. We propose a new formula, first to control the learning factors C1 and C2, and also a new formula to change or alter the inertia weight. Ideally, and briefly speaking, what we do is we start by increasing C1 and slightly decreasing C2 in the first phase, and then towards the end we do the inverse. We start increasing C2 and decreasing C1. Why we do that is because if you look at the equation, you see that C1 tends to pull the particles towards PV. So this is the exploration phase, and when we increase C2, C2 tries to pull the particles towards the best global solution, and this is the exploitation phase. And so we balance it through this control logic, altogether with this new formula to update the inertia weight, which benefits from an exponential decrease instead of a linear decrease. It's worth saying that smaller values of the inertia weight accelerates the convergence of the algorithm. And so the total approach, just like we did with the Ph.D, is shown in figure 1. So we use our new proposed PISO to optimize different parameters of the MPC, namely the prediction horizon, control horizon, weighting matrices Q and R, and also the number of Laguerre terms that we use. Again, the PISO only looks at the tracking mean squared error to predict the best optimal parameters. We have tested our proposed PISO algorithm on a standard 5D sphere function and compared it to other improved versions, illustrated here. After running the algorithm to solve this equation, after 41 iterations, our proposed method was able to reach a minimum cost of 10 minus 3 compared to 2.1, 3.1, and 5.51 from the other versions. So clearly in the figure you can see that our proposed method is faster and also produces more optimal solutions compared to the other methods. And now the idea is to do the same way we did for the longitudinal control, perform multiple simulations with the proposed PISO algorithm while changing the working conditions, for instance, changing the longitudinal speed between 3 and 27 meters per second, lateral position between minus 15 and 15 meters. And after we do the optimization, we'll generate a data set, which we'll then use for the adaptation. And here we have tested our generated controllers for 3 scenarios. The first scenario, a double lane change with varying velocity Vx. So the profile of the velocity is shown in figure 1 for this scenario. Scenario 2, a general trajectory with varying velocity profile shown in figure 2. And scenario 3 is nothing but scenario 2, but we include wind gust as disturbance, which is shown in figure 3. And these are the results we have obtained. So you can see the trajectory of the double lane change in figure 1, when we are comparing the standard MPC and our approach, which we call AMPC, for adaptive MPC, with a standard controller, pure pursuit controller. Well, you can notice that once we start changing the longitudinal velocity, the pure pursuit controller is not able to cope with this and diverges, whereas both standard MPC and adaptive MPC are able to track the trajectory. But the interesting thing is that the recorded or the obtained mean squared error for our approach is as little as 0.12 compared to 0.48. So the tracking accuracy is much improved. in figure 2, you see the control signals for the different controllers. Now we move into the results of scenario 2. So the general trajectory is again shown in figure 1, and you see a similar trend, so both NPC and AMPC are able to track the trajectory. But similarly here, with much more accuracy, with an MSE of 7.20 compared to 25 for the standard NPC without adaptation. If you look at figures 3 and 4, you see the adaptation signals. So these are the changes in the parameters of the controllers throughout this test. So Q and R adaptation are in figure 3, and the other parameters are shown in figure 4. This is the result for the last scenario where we include the perturbation, and in this scenario we notice one thing is that above certain speeds of the wind, above certain levels of the perturbation, even the standard NPC is not able to reject them and diverges, as shown in figure 1, whereas our controller is able to reject the disturbances and track the trajectory with minimum deviations. Okay, so far we have utilized the same approach with lookup table and dataset. What we propose in the next step is using the power of AI to learn that data and replace them with first a neural network and then an adaptive neural fuzzy inference. Why we choose adaptive neural fuzzy inference is because we had the aggressivity problem using neural network with the Ph.D. And so in this time around, we are trying to adapt only 4 parameters, so the weighting matrices Q and R, and prediction and control horizon of the NPC. For the first approach, we propose to use 4 simple neural networks for each parameter, containing 2 hidden layers only, with 16 and 8 hidden neurons respectively. And the inputs to the neural networks are only the lateral position, longitudinal velocity, wind speed, and this time around we add another parameter which is mu that represents the road friction coefficient. Similarly, in the second approach, AMPHIS-NPC, we use a general AMPHIS system composed of 4 AMPHIS subsystems for each parameter. We train the AMPHIS using a hybrid training method with gradient descent and recursive least squares to avoid local minima. And we use input space partitioning with the scattering method since we have multiple inputs. So for this case, we do the same optimization with Bissell, but we include the mu parameter, so the road friction, which we vary between 0.5 and 0.9, which is supposed to represent the road condition whether it is wet, very wet, or dry. And we test our controller in 2 scenarios. The first scenario is a triple lane change with varying velocity profile shown in figure 1, wind gust profile shown in figure 2, and adhesion coefficient shown in figure 3. The second scenario is a little bit more complicated, whereby we test our controller in a general trajectory with a very demanding, well, not very demanding velocity profile, but excessive wind speed profile and also road friction profile, as illustrated in figures 1, 2, and 3. Once we test our controller, we obtain these results. So the triple lane change trajectory shown in figure 1. So first of all, this is often performed in multi-lane highways where we change lanes successively. So as you can see here, we are comparing the standard NPC with our NN NPC and AMPHIS-NPC. And when you zoom on the signals, you see that there is much more tracking accuracy to NN NPC and AMPHIS-NPC compared to the standard NPC, which is further illustrated in figure 2, which represents the tracking error, and also by the recorded mean squared errors. So NN NPC and AMPHIS-NPC scored as little as 0.005 compared to 0.3 for the standard NPC. And figure 3 shows the control signal, which is the steering input for the 3 controls. Figures 4 and 5 show here the adaptation signals for the different parameters using both NN NPC and AMPHIS-NPC. And what you immediately notice compared to the previous approach, we have much more adaptation happening here because using neural networks and AMPHIS systems makes this approach more general. and so it's able to cope with much more working conditions. We have noticed that the control algorithm tends to increase the prediction horizon and control horizon whenever the working conditions become tougher, and whenever these conditions are relaxed, then these values are decreased. So a similar trend in scenario 2 is observed. Same thing, all the three controls track the trajectory, but with different levels of accuracy, with NNMPC and FSNPC much more accurate, recording 0.13 compared to 0.58 for standard MPC. And these in figures 5 and 6 are the adaptation signals for all the parameters that we adapt. Okay, so what we can say about the contributions for the lateral control is, first of all, the adaptive MPC with Laguerre functions does provide better tracking performance compared to standard one due to the adaptation. It only utilizes the simple bicycle model, but does require offline optimization with the PISO and also approximation for the pivot table adaptation approach. As for the NNMPC and FSNPC, both are much more accurate compared to the previous approach, with the exception that NNMPC provides slightly better tracking than FSNPC and very fast computations, whereas NPC provides smoother control, but it is very heavy in terms of computation, and in fact, it's not applicable in real time. Now we move into the third contribution, which is the coordinated lateral longitudinal control, by which we coordinate a longitudinal control with a lateral control to achieve autonomous driving. And here, for the modeling, we reuse the same model, but this time around, instead of using genetic algorithms, we reuse the proposed improved PISO algorithm, because we have found that it runs much faster than the genetic algorithm. So it's the same approach, whereas for the lateral control, we reuse the same bicycle model, but this time around, we use an LPV formulation, whereby the state matrices A and B are LPV and depend on a scheduling vector. As you can see, all the terms depend on the scheduling vector as well, which is in function of certain parameters such as the longitudinal speed and also the cornering stiffness coefficients. Now, when we are using purely linear systems, these cornering friction coefficients, CF and CR, for the front wheel and rear wheel, are constant. But in reality, they change with time. And so this is what we propose to do to adapt the prediction model of our controller, of our NPC controller. And how we obtain those cornering stiffness coefficients is by using a recursively squared estimator that would require information from a simulator. In this case, we used CarSim. This information represented the lateral forces of the tires and also slip angles, and it will produce CF and CR following this set of equation where Z here represents the measured values, theta the estimated values, and phi represents the regression vector, with E being the identification error. Then we model the same way we do. We formulate our model predictive controller, but this time around using an LPV prediction model, and we further add another contribution to improve the cost function, and this contribution is in the form of an exponential rate represented by beta here that decreases with the number of iterations. What this does is that it puts more focus and gives more importance to the immediate control actions compared to the future control actions. And so this way we penalize more immediate tracking errors. And we add another slacking term represented by epsilon to ease the optimization problem and avoid infeasible situations. And this is the coordination approach. So you can see that our PISO PID will generate either acceleration or braking sent to the simulator. Our LPV NPC generates the steering angle, but it does require information from the simulator about the longitudinal velocity and also about the cornering stiffness coefficients coming from the recursively squared estimator, which uses information about lateral forces and slip angles coming from the simulator. Now, to ensure the lateral stability, we input constraints on the longitudinal speed. First is represented by the first formula here. So the longitudinal speed must not exceed a certain value that is in function of different parameters, such as the gravity G, the camber angle, the road friction coefficient, and more importantly, the curvature of the road roll. The second constraint is on the side slip angle in function of the longitudinal slip, as represented by this equation. But in the model, we don't have access to side slip angle, but we can represent it in the terms of the steering angle delta F for the front wheel. As delta R is equal to 0, only the front wheel is steerable. So we can reformulate this condition to impose a constraint on delta F instead to ensure that this constraint is met. And finally, we test this control approach on a double lane change and general speed profile. So figure 1 shows first the disturbance in the form of wind profile wind velocity profile, sorry. And then in a speed profile that the vehicle needs to follow, and in the third part of the figure we have the control signals, the generated control signals. We have recorded a minimum MSE of 0.02. In this case, you can see that the Ph.D does an excellent job following or tracking the velocity profile despite the disturbance that was injected. As for the lateral tracking performance, it's given in figure 2. You can see that here we have the lateral position tracking performance, heading tracking performance, and also the control signal. And what we observe here is much more accurate tracking. In fact, the MSE value for our approach, LPV-MPC, which we call here Enhanced MPC, short for EMPC, records an MSE of 2.1 to 10 minus 4 compared to 0.6 for the standard MPC. While the heading tracking MSE is as little as 1.10 to 10 minus 4 radians compared to 6.75 to 10 minus 4 for the standard MPC. Then we test another scenario, which is a general trajectory represented here in figure 1. And the idea is just to test if the controller can track this trajectory. And you have in figure 2 the lateral tracking performance. And as you can see, it does an excellent job tracking both heading and lateral position. With an MSE of 0.3 for lateral position and 6.5 to 10 minus 4 for the heading tracking. The other part, which is the longitudinal control. So here we illustrate the used speed profile in this figure right here with the disturbance wind profile. And as you can see, we see a similar trend. So even the longitudinal control is doing a great job. In figure 2, you see the estimated coronary stiffness coefficients for both wheels that change during this scenario. Okay, so what we can say about this approach is that LPV-MPC for lateral control greatly improves tracking performance because it uses an adaptive prediction model, but one downside, it requires information from the simulator for the estimator to estimate the coronary stiffness coefficients. Whereas for this OPID, it does provide good speed tracking, but it's not adaptive because it was optimized only once, and it does require offline optimization. And now we move to another contribution, which is coupled lateral and longitudinal control. What we did before was coordinated lateral and longitudinal control, developing different controllers for different tasks. But here we developed one controller that handles both tasks by using a more elaborate model that couples both longitudinal and lateral dynamics of the vehicle. So the model is expressed by the 3 sets of equations given here. The longitudinal and lateral dynamics are in the first set. In the second set, you have only the lateral tire forces and the drag force, and in the third set, you have an extra layer of vehicle kinematics. And this one is to further ensure more precise tracking, which is nothing but the lateral position error and the heading error. So the engine for the longitudinal dynamic is a simplified model represented by the first equation right here. So you can see that this model is nonlinear, so we can present it as a nonlinear function of the state vector x, input control u, and curvature k. So here k represents the road curvature and it's an external parameter. We can reformulate or transform this model into a state space model, an LPV state space model whereby the state matrices A and B would be in function of a certain scheduling vector, which is illustrated right here, phi. And you can see that this scheduling vector contains endogenous and exogenous parameters. The only exogenous parameter is K, which is the curvature, road curvature, and the others are only states and control signals. The matrices are illustrated right here, and similarly you can see that in all the terms of the matrices we have the cornering stiffness coefficients that reoccur. And later on we will propose a new approach to adapt those cornering stiffness coefficients. So then we formulate our more elaborate LPV MPC using the more elaborate dynamic model that combines both longitudinal and lateral dynamics. And we just formulate our control problem as an optimization problem, the standard way as we did before. This time around, we want to optimize only the weighting parameters of the cost function to further enhance its performance. And you can see here that we have added another term, which is a terminal cost. That's to further ensure the controller stability. So what we propose using now to optimize those weighting matrices is another improved genetic algorithm. We use the standard one for the PID, but here we try to improve the performance of the standard algorithm. And ideally, during the selection operation, a standard genetic algorithm uses only one selection operation. This can be roulette wheel selection or tournament selection. Both have advantages and disadvantages. For instance, if we use only roulette wheel selection, then the algorithm tends to reuse the same prominent genes over and over, and this causes premature convergence. Whereas for tournament selection, we have the choice to choose the selection pressure, and then we have more options for, or more chances for even weak genes to be selected. And this ensures better overall search capabilities and also gives more chances to attain more goal solutions. And so what we propose to do, or our little contribution here, is a modification of the standard algorithm in which at the beginning of the algorithm we generate two random percentages for both operations, and then we compare those random percentages. The highest percentage gets picked and we perform the corresponding operation. So let's say at iteration I or K, the percentage of roulette wheel selection is higher than we perform roulette wheel selection. The next iteration we recheck if tournament selection gets chosen, then we perform tournament selection. And then we compare this improved genetic algorithm with a standard algorithm using only roulette wheel and another one using only tournament selection. And as you can see here, so the test was the same 5D sphere function as the benchmark. And you can see here that there is not a huge improvement, but still we can see that our algorithm is a little bit faster and a little bit more optimal. So this presents a small contribution to the performance of the optimizer genetic algorithm. And as I said before, so all the terms of the matrices contain the cornering stiffness coefficients, which we need to update to make the prediction model adaptive. For this case, we propose using a neural network to learn to predict those parameters, because in the previous case we used an estimator that requires information from the simulator. But in this case, it will only be done by the neural network. So first, we need to train that neural network, and so we need data. So what we did is we performed multiple driving scenarios in car sim to generate a data set. We record the data. In fact, we were able to generate around 10,000 data points, which then we split into 25% for testing and 75% for training. And we train our neural network. The best architecture that we found was using a deep neural network with 4 hidden layers, containing 16, 28, 16, and 9 hidden neurons respectively. And as you can see, the inputs to the network are only known parameters, or at least measurable parameters, which are nothing but the states and the control signals. And the outputs are the cornering stiffness coefficients. So once we develop our model and train it for 2005 epochs with a learning rate of 5 to 10 minus 4, using Adam and a batch size of 64, it resulted in a training loss of 0.19 and a validation loss of 0.22, which is then translated into an R2 score on the training data of 88% versus an R2 score on the testing data of 78%. And you can see in figure 1 that the neural network is able to learn the data without overfitting, Whereas in figure 2, we compare the predictions of our learned model against the true values, and you can see that it does an excellent job. It's not 100% correct, but it's able to predict those correlating stiffness coefficients. So we tested this control approach using the coupled model, adaptive MPV-MPC, which we call here MPV-MPC, and we compared it to the MPC controller of the previous approach. And as you can see here, once we zoom on the tracking of the same trajectory, you see that actually the MPV-MPC of this approach is a lot much accurate. And this is because we coupled both lateral and longitudinal dynamics. In fact, the MSE score of MPV-MPC was as little as 0.02 compared to 0.3. And figure 2 represents the tracking errors for the longitudinal speed, lateral position, and heading. And maximum errors are given right here. So as little as 0.08 meters per second for the speed, as little as 8 centimeters for lateral position, and around 11 degrees for the heading. Now we move into the longitudinal part. So we are trying to follow the velocity profile given in figure 1, subject to wind disturbance given in the top part of the figure. And here we are comparing the PISO PID against the same MPV-MPC. And you can see a similar trend, so MPV-MPC is much more accurate. And finally, figure 2 shows the predicted cornering stiffness that adapt the prediction model of the MPC. One interesting feature is the computation time. So this approach is able to run in real time. It's very fast. All the prediction and optimization phases run at around 0.01 seconds. And so it's more than a real-time application. What we can say about this approach is it provides a higher tracking accuracy compared to all the previous approaches. It has been optimized using an improved genetic algorithm, and also it runs fast online. But it does suffer from one thing, is that the LPP formulation requires instantiation, which can be solved using primers or previous MPC predictions. Now briefly I'll speak about the last contribution. Briefly speaking, what we propose to handle the autonomous racing task is a learning-based controller. This time around we use a nonlinear model predictive controller coupled with a nonlinear moving horizon estimator that will estimate vehicle states. Both use a simple kinematic nonlinear model. So it's a reduced and low order model so as to allow us to run both MHE and MPC in real time. Then we propose an offline MPC planner to generate the optimal racing line. But this time around, the MPC will use the full nonlinear dynamics of the vehicle, which represents the actual vehicle, and which is why it is run offline, because it's not real-time applicable. And because we are using a low-order model for both the controller and estimator, what we propose to do to enhance the controller performance is add on top of that a Gaussian process regressor, sort of as a learning extension. And what we do is, what this Gaussian process regressor would do is just predict the error between the prediction model of the MPC controller and the actual vehicle dynamics, which is represented by F error here, which is nothing but the difference between the two models. And so, since we have 4 states in the kinematic model, then we would need 4 Gaussian process regressors. And once we predict that error, then the correction would be the learned model, which is nothing but the prediction model of the MPC plus the error that has been learned using Gaussian processes. Now, I will not speak about this in detail since we are short of time. This is a work in progress, and the idea is to perform this control approach on a miniature car, a 1 to 10 scale car, to perform this racing action, because it's very hard to apply it on real vehicles. And the goal here was to apply it on this miniature car, which is a Q-car Conzer. So far, the goal was to for our lab to obtain this car. We have already ordered it, but until now we have not received it. So instead we just performed simulations, and here we show you some preliminary results. So we tested this control approach, the whole scheme with moving horizon estimation and learning extension on a racing lap or track, as you can see in figure 1, that has an L shape. And here we are comparing NPC with standard NPC without the learning extension. So in red you have the generated optimal racing line with the nonlinear NPC planner, and in blue you have the learning-based NPC, and in dotted line the standard NPC. And you can see here that actually the NPC with learning extension is able to drive much more aggressively, cut corners sharply, and also run faster. This is further confirmed by the recorded root mean square error for the learning-based NPC for as little as 0.09 meters compared to 0.12 NPC without learning extension. Whereas the average speed was recorded at 2.51 meters per second for the NPC against 2.14 meters per second for the standard NPC. It's worth noting that the cars here are miniature cars, so the speed of 2.5 meters is actually a large speed, so it's a racing speed for that scale. And here I present in figure 2 and 3 the signals, the control signals, which are the steering and the acceleration. And you can see for LMPC they are much more aggressive due to the corrected prediction model, the learning extension, whereas you see the speed profile or the velocity profile of the vehicles in figure 4, the racing speed. Finally, to conclude, so throughout this thesis we have proposed an approach to handle optimized adaptive longitudinal control using self-adaptive PID with 2 approaches, NNPID and GNPID. We then worked on the path tracking application by proposing an optimized adaptive NPC with Laguerre functions, and then an NNNPC and ANFIS NPC. Then we tackled the coordinated control approach by coordinating LPV NPC for lateral control with PESO PID for longitudinal control to ensure autonomous driving. And then we further moved into a more difficult task, which is the coupled lateral longitudinal control with a more elaborate LPV NPC. And the final contribution is using a Gaussian process learning-based nonlinear NPC with nonlinear moving horizon for a more complicated task, which is autonomous racing. Throughout the course of this thesis, we have been able to use and improve several meta-heuristic algorithms, namely genetic algorithms and PESO. And we have also enhanced and improved classical controllers using different learning techniques, including neural networks, MLPs, ANFIS, and Gaussian processes. As perspectives, what I can propose is that we can still replace the lookup table with a machine learning approach for the first approach, using GAPID instead of the lookup table. Also, the NNPID was very aggressive and would likely induce jerk effects, and so we propose using fuzzy inference systems to smooth out the control signals. We have only used the mean squared error as a cost function for the GA, and several other cost functions can be investigated and would yield more optimal solutions. For the LPV approaches, so here we are using only constant scheduling vectors, so the parameters are constant. This can be improved by including varying parameters such as a longitudinal speed that change as we move throughout the prediction horizon. And finally, when we adapt the cornering stiffness with normal neural networks, we don't improve temporal dependencies. This can be remedied using recurrent neural networks. And in fact, we have done this in a new scientific production, but it's not included here. As a last perspective, we can still improve the estimation of the moving horizon estimator by using a more elaborate model instead of the simple kinematic model. And these are some of the scientific productions that were published throughout the course of this PhD. So we have published 5 IEEE or 6 IEEE conferences, and one journal article in the Asian Journal of Control. We still have 2 submitted articles, one for the European Journal of Control being reviewed, and another one for the same Asian Journal of Control, which is still being reviewed. And with this, I conclude my presentation, and thank you very much.